Hello and welcome to Chemical Guruji channel. Today we are going to discuss about the Sabatier and Sanderens reaction. In this reaction, we are going to discuss about the reduction or hydrogenation of unsaturated hydrocarbons, for example alkenes, alkynes, in the presence of hydrogen and catalysts. So this is alkene, and alkene is getting reduced in the presence of hydrogen catalysts, and it will give alkane. Similarly, alkyne will also get reduced in the presence of hydrogen and the catalyst, and it will also give the alkane. Here we can see minor difference that in this reaction, in this reaction of reduction of alkene, there is a requirement of one equivalent of hydrogen, and here we can see in the reduction of alkyne there are requirement of two equivalent of hydrogen. Now let's see what are the catalysts are. So there are number of catalysts in this reaction is being used: palladium, platinum, nickel, nickel. So for the palladium and platinum, there is no extraordinary temperature or pressure is required, and for nickel, there is no requirement of additional temperature. The reaction can undergo in the presence of nickel at room temperature, but for nickel only, there is requirement of 200 to 300 degrees centigrade temperature is to be maintained to get the reaction completion. Okay, so what is the nickel? If you want to know more about the nickel, I have given link in the description, and you can add more knowledge from that link. Here also I have added some points. So nickel is obtained from the boiling of nickel and aluminium mixture with alkali sodium hydroxide. The process is known as quenching. In this quenching process, aluminum is getting dissolved and nickel will be obtained as finely divided state. One more point is to be noted that in this reaction we cannot prepare methane because the smallest unsaturated hydrocarbon has two carbons like ethene. So the smallest possible alkane which we can get from this reaction is ethane. So methane cannot be prepared from this reaction. And let's see the reaction mechanism of this reaction. Let's see the reaction mechanism. In this reaction, alkene or alkyne is getting reduced in the presence of hydrogen and catalysts. So here we can see this is alkene and this carbon is sp2 and this is also sp2 carbon. So this is planar. Okay, and in the presence of catalyst, it will get reduced to the alkene. Here we can see we have got syn product. What do you mean by syn? Syn is very simple. These both hydrogen are added from the same side. Like here we can see this hydrogen and this hydrogen both are below the plane. So here the stereochemistry of this reaction will play a very important role. So how the stereochemistry is important and why these are getting attached from the same side and giving same product. Let's see. Let me explain you more. This is metal surface of the catalyst. This is the catalyst and these are the activated hydrogen. So now the substrate, which is unsaturated hydrocarbon. This is the substrate. Okay, in this substrate I can see that this carbon and this carbon is sp2 and the structure is planar. So this is planar, the metal surface is planar, so it will approach from one side. So both the carbon will get exposure from one side only. Okay, so I can see this is sp2. Okay, and now this metal surface will be approached by the substrate from one side and it will give product like this. So hydrogen is getting attached from same side like this. Here it is sp2 hybridized. These are the sp2 hybridized carbon and this is sp3. So hydrogen, so after attachment of the hydrogen, the hybridization is getting changed from sp2 to sp3. So this is also very important point to remember that whether the hybridization is getting changed in this reaction. Yes, hybridization is getting changed from sp2 to sp3. This is the reaction mechanism, and in this reaction mechanism you will get exposure of stereochemistry and hybridization process also. One more point you can note it, that hybridization is getting changed from here to here in this process. So whether the oxidation state is getting changed or not. So you can pause the video and you can get it done with your knowledge. Otherwise, I'm going to discuss in next slide. Okay, these are the, let's take a few examples. So in this reaction, we know that alkene and alkynes are getting reduced to give the product as alkene. Both will give a product as alkane. Complete hydrogenation. So this is the alkene and this is ethene. Okay, in ethene will undergo reduction. Okay, so heating is requirement, as we discussed it. For nickel there is requirement of 200 to 300 degree centigrade temperature. Okay, so we have given the temperature and we can see this pi bond is getting replaced by sigma bonds. Two sigma bonds are being formed with the catalytic hydrogens, and here there are two pi bonds, so two equivalent of hydrogen is required to get it reduced in alkane. Let's see the next example. In this example I'll explain you something more aspects of this reaction. So this is alkene and alkene is getting reduced in the presence of catalytic hydrogen, and so we can see that hybridization is getting changed. This is sp2, this carbon is sp3. Okay, and I can draw like this also. So the question is, does oxidation state and hybridization state changes in this reaction process? You can pause the video and get it done with your knowledge. I'm going to discuss it with next slide. This is the example. So in this example, we can see the red dots. These red dots are electrons. As we know that one bond is made up of two electrons, like this. These red dots are electrons. I have denoted like this to have better clarity. So we will find the the oxidation state of sp2 carbon. These are the two sp2 carbon. So we will find electronegativity of sp2 carbon. Okay, and as we know that electronegativity is getting decreased from top to bottom in the periodic table, and from left to right in the periodic table it is getting increased. Okay, so with the help of oxidation state, with the help of electronegativity, we will calculate the oxidation state. Here, see, this is this carbon and this is carbon. Electronegativity of both carbon, this carbon, this carbon and this carbon. Electronegativity of both carbon is similar. Okay, this carbon, electronegativity similar. This carbon and this carbon, electronegativity different. There is no difference in the electronegativity. This carbon and this carbon, no electronegativity difference. This carbon and this carbon, no electronegativity differences. So here I can see that this carbon has these 4 electrons and this carbon has these 4 electrons. So can I say that oxidation state of these carbons are 0? Okay, 0. Let's see the product after the catalytic hydrogenation. Okay, here we can see this carbon and this carbon 0, this carbon and this carbon 0. For this bond I can see that electronegativity of carbon is higher than that of hydrogen. So this is -1, this is +1, and here because of this bond 0 and 0. Because of this carbon and this carbon 0 0, this carbon and this carbon 0 0, this carbon and 0 0, but this is where there is a difference of electronegativity, so electronegativity of hydrogen is less than that of this. Okay, so can I write it that oxidation state of this compound is this, and this compound is oxidation state of this compound. For this compound, carbon has -1 oxidation state. This carbon has -1 oxidation state. Okay, so what we can see? We can see that the oxidation state is getting changed under this process from 0 to -1, means it is getting reduced. So oxidation state is getting reduced, that means it is reduction. So the process is reduction process. So this process I can say that this is reduction process. So I can say this reaction is reduction reaction. Let's discuss about the cycloalkanes. So this is cyclopropane, and cyclopropane is getting reduced in the presence of palladium or platinum or nickel, and it will give the propane, that is non-cyclic product. Okay, so this is non-cyclic and this is cyclic alkane. Cyclic alkane is getting reduced to non-cyclic. Why? Because of angle strain. We will study further that what is the reactivity order of the cycloalkane for this reaction. Okay, so in this reaction this bond is broken and it is converted into non-cyclic alkane. Here also this cyclobutane is getting converted into butane. Similarly, you will think about this reaction that this cyclic compound will be converted into non-cyclic hydrocarbon, but it will not happen here as it happened in the previous slide, because these compounds are more stable, so there will be no reaction. what will happen with this reaction? With this propene, this propene has angle strain, and we have seen reaction with the propane, cyclopropane. So in this in cyclopropane, there were requirement of only one equivalent of hydrogen, but here, because of this double bond, one more equivalent of hydrogen will be required. So total requirement of 2 equivalent of hydrogen for this reaction, and we will get propane. Why no reaction? Because of reactivity. Let's see the reactivity order. Cyclopropane, cyclopropane, cyclobutane, cyclopentane, and cyclohexane. So this is more reactive. More reactive. Why? Because of more angle strain. We know that there is angle of 109 degree and 28 minutes, which is stable in hydrocarbons in sp3 hybridization. Okay, so here we can see only 60 degree, so there is angle strain. Here we can see 90 degree, so there is angle strain. But here the structure is different. There are so many conformations for pentane, like boat-like structure, and so strain is getting reduced. That's why it is not that much reactive, and it is stable, and this is also stable in form of conformers. Yeah, let's discuss about some more important examples. Let's see. This is cyclic unsaturated compound, and this is 6 carbon ring. So there is no angle strain. So you will say there will be no reaction. But no, it's not like that. Since there is pi bond is present in this compound, so it will give opportunity for this hydrogen and platinum to get it reduced. So we will obtain this product, and we can see this carbon and this carbon is chiral carbon. Okay, so we can see that this hydrogen will attack from, this hydrogen can attack from above the plane as well as below the plane, like this. So what we will get? We will get enantiomers. These both compounds are enantiomers to each other. You can see this and this. These both are mirror image. So can I write here? These are mirror image to each other. So this is also very important reaction. Reactions are very simple, only concept based reactions. So this is alpha pinene. This compound looks like ship. Ship is obviously it will land on dockyard. So this is the dockyard. Dockyard means it is not actually dockyard, it is catalyst. Okay, so here the ship, the alpha pinene will approach from one side only, like this. It will not be able to approach from both sides to get this pi bond reduced under the catalytic hydrogenation because of steric hindrance of this group. There is a steric hindrance, so we will not receive any enantiomers as a product. We will receive only product, not the mixture of product as we have received in the last slide. Okay, so hope things are clear, and please do like, share and subscribe.